Okay, guys, a little bit different this time. Unit 3, Day 5. This is the end of Chapter 1. So we will continue with probability in the next couple of days, but not from Chapter 1. It'll be Chapter 2 and Chapter 3. What's different is what I've done is I've scanned my class notes. So instead of scribbling everywhere, I'm going to point at my scribbles from class. So hopefully this makes a little more sense. Probably not, though. But we'll see. So we've looked at independent events in the past, and we're going to look at them here. So independent event, we drew a tree here about having a male or a female as offspring. You want to have 3 kids. So you go through this and you have a male or a female. So we first initially drew the tree like this with M and F on every branch. And then we went through it and we talked about the probability of certain things happening. So the probability of having 3 males would just be, you count the number of branches where you had 3 males. So this was the only branch that had 3 males. So that's 1 branch, terminal branch out of the 8 branches. So 1 out of 8. So again, for probability, it's the number of successes, number of times you see success over the total number of trials. Okay. So here there were 8 trials, or here there are 8 trials, and 1 of them is success, and 1 out of 8 times is that those 3 males happen. But then later what we did was we noticed that, or we got to the point where we said, let's put probabilities on the branch. So in this case, it's a little bit boring because each of the branches has a 1/2 put on them because there's a 50-50 chance of a male or a female. And what you can end up doing is if you want to end up over here by following this branch, the probability of getting here is 1/2 times 1/2. You just multiply this times this times this. So 1/2 times 1/2 times 1/2, which is 1/8, which is the same answer as this. So you can either, in cases where it's 50-50, you can just count that. You can use a tree to count the number of ways things can happen, and do it the way we did earlier, number of successes over total number, or you can use the probability on the tree. So on page 2, as we kept going, this is where it gets a little more interesting, and why you use a tree is because what happens when it's not 50-50, but the numbers are different. So here we drew a spade, and then we rolled a die, and we drew a card, and we figured out, am I drawing a spade or not, S or S prime? A quarter of the cards are spades. 3/4 are not spades, so 0.25 goes here, 0.75 goes here, so this is 1/4 and this is 3/4. Okay, that's how let's write them as decimals this time. And then after that you roll the die, and half the time or 0.5 times you get even, and half the time or 0.5 you get odd. And that's the same with this and this. And then if you want to figure something out, so for example, let's say I want to figure out what is the probability of drawing, and let's see what we did here. I don't know. Let's just do this here. Let's say, what's the probability of drawing a spade and an odd card? What you would just do is go from here to here, and then follow the branches and multiply the branches probabilities by each other. So here, I would go 0.25 times 0.5, and I get 0.13. So 0.25 times 0.5 gives me this number when rounded, which means the probability of going spade and odd are 0.13. And if you went through the entire tree, you could figure out all the probabilities given the data here. Okay, so that's interesting also. But these are what we call independent events. Dependent events, or conditional events, conditional probability based on dependent events. So those two terms kind of go together. What happens here, the difference is the result of one trial affects the probabilities of subsequent trials. So what we're talking about is this. Something happens, and then depending on what happened, then different probabilities arise for the next situation. So the easiest way to do this is when you look at a deck of cards, and you take a deck of cards and you take cards out and don't replace them, you're changing what's left in there. So very simple. I didn't use 52 cards. I just said let's have 8 cards, and 8 of them, of the 8, 3 were black and 5 were red. So when you draw your first card, you have a 3 in 8 chance of getting a black card and a 5 in 8 chance of getting a red card. Okay, so 3, 8, and 5 8s. Okay, success, black, 3, total 8. So 3 out of 8. Here, 5 out of 8. Now, if I'm going to draw my next card, I can have a black or a red, and a black or a red. But things are different. If I drew a black card, then I'm left with, if I had 3 different black cards, and they're all different, but let's just do this right now, and 5 red, whatever they are, the 2, the 3, and the 4, the 2, the 3, the 4, the 5, and the 6, whatever. and I drew a black card, that guy's gone. Now I'm left with 2 black cards out of a total of 7. So success happens 2 times out of 7. So I only have 2 of 7 cards that are black, 5 out of 7 are red. That's fine, but what's different is if I drew a red card for the first draw instead of a black card. So here is all drawing a black card. What happens then? Let's go back. Here's my B, 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 my R, 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 3 black and 5 red. Now I'm not scratching out a black card, I'm scratching out a red card. So now if I say what's the probability of getting a black card? There are 3 out of 7. So it's different than 2 out of 7. It's conditional. If I drew a black card originally, there are less black cards to choose from. There are more here if I drew a red card. Okay, so the odds change conditional of the other one. Okay, and what we call this, and I'm going to show you in the second case, this one here to go red and black. Okay, that there is, so this is the probability of red and then black. Okay, that's equal to the probability of red, which is 5/8, times the probability, and this is a little different, of black given red. So I already drew a red. Knowing that I drew a red, what's the probability of drawing black? That's how I write that there. Because you don't really have a second chance probability of red, because this is a, second chance, let me reword that. The second draw is black, right? So if I say, what's the probability of drawing a black card on the second draw, there's no real answer to that, because it's a 2/7 chance here and a 3/7 chance here, but that's all conditional on the first draw. So you can't say it's 2/7 and 3/7 or 2.5/7, 2.5 out of 7 or anything like that. You have to say, look, if you're asking me what the probability of drawing a black card on the second draw, what happened on the first draw? Did I draw black? Then sure, then it's 2/7. Did I draw a red? Then it's 3/7. So this is, so if I'm looking at this right here, the probability of a red and a black is the probability of a red and the probability of a black given that I already drew a red. So that's 3/7. So to work this out, it's going to be 5/8. You just go down here, 5/8 times 3/7. Okay, so that might have been a little more confusing than it had to be. You still follow this out. You follow the branches and you multiply the percents by each other. Hold on, another announcement. And when you multiply those together, remember, today you guys were a little bit sluggish with your fraction multiplying. It's 5 times 3 is 15, 8 times 7 is 56. Okay, and then you can change it to percent if needed. So let's just do the last question here. That's conditional, that's the overall conditional. Here we have a situation where 32% of the men have this gene for baldness, and if they have the gene, they have a 95% chance of going bald. If they don't have the gene, they have a 1/4 chance of going bald, which is 0.25 or 25% chance of going bald. So let's draw this here. You say, look, do we have the gene or not? The gene happens at 32% of the time, or 0.32. That means 1 minus 0.32, which is 0.68 of the time I don't have the gene. If I have the gene, so this is conditional on having the gene, I go bald 95% of the time if I have the gene, and then if I don't have the gene, then I must not go bald, or bald prime, which means not bald, 5% of the time, or 0.05. So that's what's left. 100% total, 95% here, 5% here. 1/4 of the time I go bald if I don't have the gene. So let's go down here. I don't have the gene. 1/4 of the time I go bald. That means 3/4 of the time I do not go bald, or 0.75. So if the question is this, if I just choose a man for random, what's the chance that he has the gene and doesn't go bald? So all you do is ask yourself this: which of these paths am I going down here? It says that I have the gene, so I have the gene, and I am not going bald, so I'm not going bald. So I do this: 0.32 times 0.05. Okay, and that's 2%. Next up, the next question was choosing a man from random. What is the probability that this man is bald or not bald? Let me see. Forget the question. Is bald or goes bald? Okay, so here, let's figure that out. Let me fix this up here. Here, I want to go bald. Okay, I'm looking to go bald here. Who goes bald? This guy goes bald, and this guy goes bald. So let's follow these down. You're going to go 0.32 times 0.95. That'll get you this number. And then you have 0.68 times 0.25. That'll get you this number. So there's a number here and a number here. And because they're just different events, you're going to add them together. So you find that out, and you end up figuring out that together they are 0.47, or just less than half the time you go bald. Okay, so that's the numbers from above, from that branch to that branch, and you get this. The last question is this: if I have 200 men, how many of them should go bald in general, or wouldn't go bald? So these are people not going bald. So if they're not going bald, well, I found out that 47% of the time they do go bald. That's kind of neat. 47% of the time they do go bald, which would mean that 53% of the time they don't go bald. So the probability of not going bald is 0.53. If I have 200 men and I want to know the total number, we haven't done a question like this, I don't think. What you're going to do is you're going to take the percent that they're going to go bald times the number of men, multiply those together, and you get 106 as your total. Okay, so if I have 200 men and each of them has a 53% chance of going bald on average, I should get 106 bald men, which is a horrifying thought to have. 106. Anyway, that's it. Quiz tomorrow on today's work and yesterday's work. Take care.